Hello guys, I'm very excited to say that this will be the start to our linear algebra journey. So this is our first video where we cover Rn space or Euclidean-n-Space and linearity. So let's get started. First we start with the Euclidean-n-Space or Rn. So what is this? So we can think of this as all ordered n tuples of real numbers. And this may sound daunting, but it's just all ordered lists of a number. So let's see. First we can have r, or r to the 1, you could say. So this just denotes the set of real numbers. It could be on a number line. You have all the real numbers in this set. 0, 1, every number you could think of. It's just a set of real numbers. R2 is our Cartesian plane, where we have our x and our y, and we can have a bunch of points. Here is basically containing every point you could think of. What is this? We could say this is 1, 2, and like it's just the whole plane. We have R3, which is an extension, and then we could think of this as the 3D plane. So we can have a point in 3 dimensions. It's basically all the points. So here we have a number. So here we have a number, like we can call it just x. This is our list or our tuple. And this is y, xy. Just got deleted somehow. And this can be denoted as x, y, and z. So Rn can just be a set like x1, x2, x3, all the way up to whatever n you would like. Now, there are 2 types of n tuples in Rn, or 2 types of lists. So we can denote it in 2 ways. The first way is what we are representing right now, which is a point. So again, like we can have a point in 3 dimensions. It's kind of difficult to show a point in 3 dimensions, but let's say this point is in 3 dimensions. It's somewhere here, and all these are points. And these can be points as well. Let's choose a different color. Points. So a point can just be denoted like in Rn as just we'll say x1, x2, x3. These are just the characteristics of the point. We're defining it. So this can be the x, the y, the z, and so on. And then we have a very important part of linear algebra where we introduce the vector. A vector. So vector, we'll call it v. Vectors commonly have this little symbol on top of it, which will tell you it's a vector. And we will define this with square brackets just to make it crystal clear. x1, x2, x3, all the way up to xn. And a vector differs from a point. in the fact that a vector we kind of visualize as a line. Instead of just a point in space, it's a line with these characteristics. So we can have a vector in R2 where we start from the origin, and in linear algebra, basically almost all the time your vector is going to start from the origin. So we have this vector, we denote it as a line, and we'll give this vector some characteristics. So we'll say that the x and the y. So we'll give this vector, call this vector v, and we will define it as, so we'll define it as 2 and 1, where this is the x at 2 and it has a height of 1. In R3, we will define a vector we can have an x, a y, and a z. So we can draw a vector here. Again, it's pretty difficult in a three-dimensional plane, and we'll give it a y component, an x component, and we will try to give it a z component. This vector v, we'll say that this is x is 2, y is 1/2, and we'll say z is also 1/2. So 2, 1/2, and 1/2. So Rn, if we want to denote a vector in Rn, it's basically just v, and then we can have x1, x2, all the way up to xn. And keep in mind that this is this is only real numbers. So for all I, or for all xi, where I is any natural number, we know that it is real. For all I that is a natural number. This is the same for a vector as well. And we will define the natural numbers here. It's a debate sometimes. We'll say it's starting from 1. So I hope that this is clear. Now let's move to linearity. So the definition of linearity. So again, linear functions are a bit different than what you've been seeing in classical geometry or whatever classes you've been taking from high school. This is going to be a bit different in the way we introduce linearity, where we will define a linear function as f, and then we will say that it will transform x to y, and this is typical of how we define functions in linear algebra. So we're saying that our input goes from x to y, where x can be a specific point in Rn, where we can transform the function from a point in Rn to a different point. So basically, we can say that x is going to be equal to Rn and y is going to be equal to Rm, which can be any different spaces. They're not points. So m and n are going to be positive integers. So this may be a little confusing, but basically this linear function is transforming this something of, say, we'll give an example, say the function f transforms a function from R3 to R2. And this may be a little abstract for now, but let's just define its properties and we'll go more in depth later. So the properties for linearity are going to be, first, we will define the property f alpha, and then we'll say A is equal to alpha f A. And then this alpha is going to scale the input. So basically the property is saying what the input that is scaled must scale the output by the same factor. So again, if we show this, we can show that, say we have a function sort of like a sine function. Say go like this. As soon as we increase this input, or we scale the input, it's going to scale the output. So we say we scale it by a factor of 2. What it's going to do is scale our output. So this is how it works. I would have drew a linear function, but again, it's a little confusing because we're going to associate linearity with the linear functions, and that's not always the case, as you see. And 2, we have the additive property, where we say we have A plus B, and going to be f of A plus f of B. So this property just splits up the inputs, and let's give an example. So our first example could just be this, basically the most simple function you could think of. And what happened? Okay, where we are going to say our function is f of x is equal to x. Is this function linear? You basically need to check these properties to make sure that it's linear. Oh, what happened here? So these are the properties. This is a function. Pause the video if you would like to try it out for yourself. Let's do it. Okay, so we will first scale x and try to prove the first property. So f alpha x, and basically by definition this is going to be alpha times x, because the input is directly mapped to the output, going to be the same. So, does this satisfy the first property? Let's see. We know that f of x is equal to x. So, alpha x is going to be alpha, and we could substitute x for f of x. F of x, and where alpha belongs to real, where it's some real number. So, we have successfully shown that it satisfies our first property. This can be checked off. Now we want to show that it satisfies our additive property. So, we have f of a plus b. What is this going to be? By definition of the function again, this is going to be a plus b, which is equal to f of a plus f of b. That satisfies our second property. So we can check this off. So thus it satisfies linearity. Now let's show another example. This may be a little bit different. We have x plus 5. Again, pause the video if you'd like to try it out. Okay, let's prove the first property. We are going to have f alpha x and define alpha belongs to some real number. So what is that going to be? We are going to substitute x with alpha x. So alpha x plus 5. Is this true? If we factor out alpha x, or alpha, we have alpha plus 5 over alpha. This does not satisfy linearity. We cannot, this is not f of x. So we already know it does not satisfy linearity. We only need to prove one of the axioms to prove that it does not satisfy linearity. So as long as you prove one is not satisfied, you basically know that it does not satisfy linearity. But we will prove the second axiom too. Or we will try to. We have f of a plus b. So what is that? That's basically a plus b plus 5. So we know we want this to be equivalent to f of a plus f of b. What is f of a plus f of b? Let's derive that. So f of a is just going to be a plus 5. So a plus 5, and f of b is going to be b plus 5. So it's going to be a plus b plus 10. So this is not equal to this. A plus b plus 5 does not equal a plus b plus 10. Thus, it does not satisfy linearity. And that was the video. Thank you for watching, and I'll see you next time.